Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to introduce John. John's from University of Washington, where he was advised by Tom Anderson and Arvind Krishnamurthy. His interests lie at the intersection of security and networks and distributed systems. He's done quite a bit with bots and understanding botnets and how they work, which he's going to talk about. Let him go ahead.
All right. Hello. Hi. I guess the mic is working. So I was told this is a 90-minute slot, so I'll try to make sure I use up all of the time. Just kidding. All right. Now that I've got you all sweating, let's start. Good morning. I'm John from the University of Washington. I'm advised by Tom Anderson and Arvind Krishnamurthy. And today I'm going to talk to you about understanding malware on the internet, botnets, and all the other bad stuff that goes on. Let me start by saying that the internet is not really a very safe place today. You don't want your kids roaming around alone there. There are a lot of prevailing problems. First, there's spam. There's over 100 billion emails a day. Everyone gets it. Everyone hates it. Estimated productivity loss of billions of dollars a year. Right? And then you have denial of service attacks. Now, these are becoming more and more powerful each day. You've got, a couple of years ago, you had one strong enough to take out a small country. And more recently, we've seen attacks against big financial institutions like PayPal and MasterCard, which caused them real dollar losses. And another thing which in today's ad-driven internet economy is click fraud. So recent studies have shown that nearly 20% of all ad clicks are fraudulent, and that's something people want to really fix. And there's also other affiliated bad stuff that happens, like phishing. So this is where they send you a page that looks like your Bank of America login page. You enter your username, password, and they steal all your money. So this, again, costs hundreds of millions of dollars in losses a year. So what is the common thread here? Turns out that the common thread for all these problems is usually botnets. Right? They provide the underlying infrastructure which allow attackers and bad guys to carry on their activities with impunity. And what exactly do I mean by a botnet here? So a botnet is a network of compromised computers that are controlled by an attacker. Now, the attacker has complete control over these machines, can use it to send whatever messages he wants and participate in any malicious activity of his choice. And since they're such a big part of the internet malware infrastructure, understanding botnets is kind of a necessary first step to understanding these threats and combating them. Right? Unfortunately, botnets are not really well mapped out today. So Windsurf would say that a quarter of all computers connected to the internet are infected and malicious. That's probably not true, but who knows. And at the height of the storm fervor in 2007, there were a bunch of news articles in September which said the Storm botnet has 50 million nodes, it's the end of the world. A month later, you had researchers actually measure and understand, and they revised it to a more reasonable estimate of 20,000 machines. So it wasn't too bad, and there's still life going on. And so what this shows is that there's a lot of confusion and fear and uncertainty and doubt regarding these botnets. The sizes, who's participating in them, what do they do, what are their operations. And our idea was to kind of throw some light on this, understand botnets better. So it turns out understanding botnets is really hard. And the reason for this, these malware authors, they do take special steps to make sure that you don't easily understand how they operate. They make use of sophisticated techniques for evasion. And reverse engineering is difficult because these bot binaries are obfuscated, primarily to prevent this sort of reverse engineering. And manual analysis is really difficult, takes a lot of time. And as you can see, there's a poor grad student who has to work hard to manually analyze these binaries. And this approach does not really scale well, at least unless you have a lot of grad students. So eventually, the problem is that there is no there is a lack of a comprehensive botnet monitoring platform, something which makes life a lot easier, right? And so that brings us to our goal. Our goal here is to build a system which can, in a timely fashion, with minimum human interaction, monitor botnets and their propagation. So I've highlighted a bunch of terms here, and let me just tell you about each of them. So we want this to be done in a timely fashion. Botnets are constantly evolving and changing, and the information about them becomes less valuable the further along it gets. Right? The information degrades quickly, so we need our things to be pretty quick. We want to scale, so clearly we cannot have the human completely in the loop, so we want to minimize the amount of human interaction required. And finally, we want to have a comprehensive system. We want to monitor not just botnets and their activities, but also the complete life cycle, how they propagate, and all the details regarding them. And this would give us information which can help combat attacks in real time. And I'll give you examples of this as we move along with the talk. So as I mentioned, there is a need for a comprehensive monitoring platform. We want to monitor the complete life cycle of a botnet. And this figure here gives you a rather simplistic view of the botnet life cycle. So you have bots which perform botnet activity, which is all the malicious things I'd mentioned. And they also try to infect new hosts, which again participate in more botnet activity. Rather simple life cycle. So in order to study what bots do and how they operate, we first started with Botlab. The focus of Botlab was to study their activities, their communication patterns, how they're organized, and how do attackers control these millions of machines. Right? And as a part of our study, one of the things we found was that this second step of infecting new hosts is in fact a rather complicated and more involved step. Okay? So traditionally, malware used to spread through taking advantage of vulnerabilities in applications or operating systems and compromising the machine. But as these operating systems and applications get more and more secure, there's definitely a push towards better security. It becomes harder to exploit these loopholes. And so attackers have been moving towards a simpler approach. So the thing is, even if your operating system is really secure, you still have the human, who is probably the weakest link in the chain. And a naive user is very likely to click on any link and install any application you ask him to. And so there has been a trend towards having more social engineering attacks in order to infect hosts and spread malware. And you just need to get someone to click on a link, and these links are spread through emails, instant messengers, and even search results. Again, more details shortly. So one of the things we found in our research was that these links which are used to spread malware typically are regular legitimate web servers that have been compromised. So these are regular websites that have been compromised and are being used to host malware. So this brings us to the question of, how are these web servers actually getting compromised? So we wanted to study this as well in order to make it more difficult for attackers to go about doing this. And a step before this is, in order to compromise these web servers, you need to first find vulnerable web servers. So the question here is, how do attackers go about finding such vulnerable web servers and then compromise them? So our goal was to kind of study this entire botnet ecosystem, study the life cycle, come up with defenses. And this brings us to the contributions. So for each of these various steps, we came up with systems which would measure, understand, and come up with defenses. And these have been over the last few years in NSDI, Usenix Security, and more recently last week at www. So let me give you a brief outline of what each of these things does. So there's SearchAudit, which kind of studies how attackers go about finding vulnerable web servers on the internet. And then we built heat-seeking honeypots, which takes it one step further. Once attackers find these vulnerable web servers, how do they go about actually compromising them? So our honeypots aim to study that. And once these servers are compromised and used to host malware, turns out attackers spread these links through search results. So the goal of DSEO was to study how these malware links are being spread through search results. And finally, we started off with Botlab, which gave us an initial picture of how botnets operate and what activities they participate in. Right. So let me start with Botlab, which essentially kickstarted our research into bots. Yes?
Hi. I think in your previous slides, you said there are four objectives. Three objectives is to in real time automatically monitor the bot activity, including its propagation. But based on what I see from this slide, it seems that they are not trying to monitor the real-time activity of a bot at scale or in the wild. It's more like, for example, the botnet probably study bot behavior in a contained environment.
Right.
Is that true?
Yes.
And the remaining three steps are mostly offline study, or
Not necessarily offline.
is it like real-time monitor all this?
Reasonably real time, as in on a daily basis.
Okay.
So these are things which run on, say, web server logs on a daily basis and come up with more information regarding how these botnets operate. So it gives us some idea of how these things operate in real time, but as a research prototype, it is not necessarily real time, but expected real time, ordered real time. Okay, so I'm going to start off with Botlab, which was a project which kickstarted our involvement with bots. And the stuff we learned here essentially led to the other remaining steps of understanding how bots operate. So what exactly is Botlab? So let's consider botnets in the wild. You have millions of infected machines, and each of these botnets talks to a command and control server. And various different botnets have different command and control servers that give them instructions on what to do. So these botnets talk to these servers, and the server tells them who to send spam to, which website to attack, and things like that. So the goal of Botlab was to kind of take a small-scale version of this and study this botnet ecosystem in a locally contained environment. Right? So we have captive bots which we are running in our virtual machines in our contained environment. We study who are the command and control servers they talk to, what are the instructions they get, what kind of activities do they participate in, what kind of spam do they send, and so essentially get a feel for what bots look like in the wild. And our approach to scaling this sort of botnet analysis was to automate it. And here what we do is to eliminate the manually intensive task of reverse engineering these bot binaries, we use a black box approach. And what's a black box approach here? We essentially execute the binary and study the external behavior. Right? And in order to do this in a scalable fashion, we need to automate this process of finding and executing these bot binaries. So what does Botlab need to do? Well, first and foremost, we need to continuously find and incorporate new bot binaries. As I mentioned, they keep evolving, they keep changing, so we need to keep track of them as they change. Then we perform some sort of initial analysis to pick interesting binaries. There are lots of malicious binaries out there, but we want the ones which are currently interested in. And in this case, we are looking at botnets that send spam. So we want some initial analysis to select these interesting binaries. And finally, we need to execute these binaries safely and collect the data that we want. Right? And the Botlab architecture is essentially the same three steps, but in a diagrammatic form. And the first step of this pipeline is obtaining bot binaries. How would you go about obtaining malware? The traditional way of collecting malware is through honeypots. So we had set up, so what is a honeypot here? The idea is very simple. You take a new machine, install an unpatched operating system, preferably Windows, connect it to the internet, and wait for 5 minutes, or maybe get a coffee. 5 minutes later, you're infected and you have a bot. You rinse and repeat this process, and you collect a whole range of these malware binaries. Right? And over a 2-month period, we collected nearly 2,000 such binaries from honeypots. And unfortunately, we did not find any of these spamming bots, which were kind of a more recent variety. And most of the bots which infected our honeypot were traditional IRC botnets, which were on the decline. And the reason for this was that this new generation of malware spreads through social engineering more than by exploiting vulnerabilities. To give you an example, here's a social engineering attack. You might receive, say, an e-card for Valentine's Day, which says you've received an e-card, please click on this link to view the card. You click on this link, it installs a binary, and you've essentially gotten infected. Another example you would find is if you visit a site and want to view a video, you occasionally find these little pop-ups which say that your current version of Flash is outdated, please click on this link and install it to view the video. You click on the link and you've just become the latest member of a new botnet. So the point here is that our passive honeypots cannot capture these sorts of attacks. So we need to augment our honeypots with active crawling. right? And for this, we essentially need to emulate a user. And fortunately, we just need to emulate a naive user who clicks OK on everything, and we get our set of new binaries that we want to deal with, right? So what is our source for getting these binaries? So Botlab gets a constant feed of spam from the University of Washington, and this is on the order of 2.5 million emails a day. 90% of all the email that comes to the university is in fact spam, and nearly 1% of these URLs point to malicious binaries or malicious executables and drive-by downloads. We crawl these links and fetch the binaries. In addition to the spam, we also get binaries from public repositories of malware and public honeypots, right? So this kind of fills in the first step of our picture, which is how do you obtain these bot binaries. And the next step is to analyze the binary. Okay. So at this stage, we have thousands of these binaries which we obtained, and we want to do two things. First, we want to select spamming bots to identify bots which send spam. And second, we want to eliminate duplicates. Unfortunately, a simple hash is insufficient to detect duplicates particularly for malware binaries. This is because malware authors frequently repack their binaries to escape this sort of hash-based detection. So what we do instead is to kind of generate a behavioral fingerprint of each binary. So we execute the binary for a while, and we log all the network connections. So we see which IP address, port, and how many packets they send. And now we do this for all the binaries, and we compare any two binaries, and if they have a similar network fingerprint, then we say that they are duplicates, right? And this can also, if we see them trying to make connections to port 25, we know that they're trying to send spam, and they are interesting spam bots, right? So at this step, we have interesting binaries that we want to monitor. Okay. So in the final step, the third step is to actually execute these binaries and collect data. So here we have an interesting trade-off between safety and effectiveness. On one extreme, we can say, we're going to let Botlab send out any traffic. This would be really effective because these bots get to communicate with their control servers. They get to do whatever else they need to do. But the flip side is that you are now adding to the bot population, and if you end up infecting some of the machines, you've got all these legal issues to deal with. The other extreme is to say we're going to make this a completely contained environment, and these bots are not allowed to make any external connections. Now this is not going to be effective because, as I mentioned earlier, these bots need to talk to their control servers or CNC servers, and unless they talk to these CNC servers, they don't really know what to do. So in our case, we decide to pick a middle ground where we say things like traffic to known vulnerable ports are dropped, traffic to privileged ports are dropped. We place limits on connection rates and data rates so that you don't participate in a DDoS attack. And since we are dealing with spam bots, we don't want them to send a lot of spam. So all the spam that is attempted to send is redirected to a fake mail server. Right? And at this step, we have a system which finds bot binaries, picks interesting ones, and executes them. The bots are happy because they get to send tons of fake spam, and we are happy because we get to see what they're trying to do. Now, most of the bots run fine. Yes?
Okay, maybe you are going to talk about what if the bots want to talk to the command control center and get some handshake before it starts sending emails?
Yes. So we do allow traffic. We only drop traffic to known privileged ports. And most of these bots, in fact, operate over HTTP. So we do allow traffic to go to the command and control servers. Yes.
Then what if that connection may compromise a web server?
That is something which is difficult to do, and that's one of the reasons we decided that this might not really be feasible in the long run. For the purpose of the study, we did look back and see that it only contacted actual CNC servers, but it is possible that it could masquerade as a CNC connection and try to compromise a web server.
How do you drop? Basically, what is the criteria you select to drop a particular connection? Because typically the connection runs on HTTP, on RC4 encryption, right? So how are you going to determine what to connect, what to not?
So we only drop all connections to privileged ports. So any ports, if it tries to connect to, say, port 3389 to remote desktop servers, we drop that, or NetBIOS ports, or ports with known vulnerabilities, those are dropped. So that would mean that we end up missing a few bots which might require this in order to get active.
So it seems that when you limit the behavior, constrain the behavior of the bots, you make some assumption about what kind of activity they're doing, what kind of behavior, what kind of rules. Like, what if there are bots which are not under your, which you don't quite understand, and your restriction actually will make the bot unusable or deviate a lot from its regular behavior?
So in that case, we would end up not seeing these bots. So we are only able to capture bots which kind of fit into some particular set of rules which we thought to be reasonable.
Among all the bots you catch, what's the fraction of them remains that conform to the rule you set versus how many of them you
So in terms of spamming bots, we are finally able to run around 11 or 12 of them.
And this is out of how many?
That we are not really sure because the others don't get to send spam. So we find 11 bots that actually send, 11 different botnets that actually send spam. And we found that this corresponds to nearly 80% of all the spam that comes into the university is from these 11 different botnets, or actually only 7 different botnets. So we do see a reasonable coverage in the terms of botnets that actually send spam.
I wonder if there's a better way for you to, without restricting the bot behavior so heavily, at the same time you still be able to have a much better coverage of the bot behavior. For example, you may just redirect all the bot traffic to some fake IP address space where you can do some.
But you would still need to have, for each botnet, you would need to figure out what is the. It would not be. The information would not be really high fidelity because now the bot is not necessarily sending spam to the people the controller wants it to send spam to, or the kind of spam that it is sending would be pretty much different. So there's definitely a trade-off between fidelity and safety, and that is a somewhat difficult line to figure out.
I might have missed this, but how are you associating spam that comes at your UDAG servers to a known botnet?
I haven't yet mentioned that, so that's kind of the next part of the talk on, based on what we study from these bots, how can you gain additional information about them. So I'll talk about it in a couple of slides. So one of the things we found here was that most of the bots run fine, but in some cases we do need to do some manual tweaking in order to get them to run. So here's an example. So one of our bots, MegaD, actually verified that it was able to send email before it got activated. So when the bot is run, it would send a test email to a specific mail server, which is controlled by the attacker. That would return a special code, which is the activation code. And the bot needed to send out this activation code to the CNC server before it got activated. And if the code was incorrect, the bot would essentially refuse to run. So in these cases, we had to allow a few connections out in order to get it to run.
So when you say your bot detection is automated, it seems that
it is mostly automated with some manual tweaking report.
It seems that in the beginning you do have to go through a lot of manual process just to write up all these rules.
Yes.
And then you can use some detection by matching the behavior with some, for example, signature that you already have. But it's not like that. Can you also automatically generate the signatures, or you can only automatically detect based on existing signatures?
It's usually based on existing signatures because you could potentially come up with a scheme to automatically detect these signatures, but that would involve letting the bot run unhindered for a while to observe its actual behavior.
But are you able to extract the signature automatically?
In terms of which?
For example, the network behavior, you said this bot has this network behavior. You use this to eliminate redundancy.
Yes.
Are you able to extract all this network
Yes.
signature?
Yeah, so each bot runs for a few minutes inside a VM. We look at all the network connections it makes, and that becomes the signature of the binary.
You use the raw network traffic as signature, or you extract certain feature out of it?
We extract features, such as the which IP address it connects to, which are the DNS names it looks up, which port does it connect to, what are the packet sizes, and use that as a signature. So this was one of the cases in which you required some sort of manual tweaking to get these bots to run. But there were a couple of other challenges which we occasionally faced. So one of the main problems was that there were some bots which would detect when they're being run inside a virtual machine and they would self-destruct. So in these cases, we needed to actually have physical bare metal boxes to run certain bots. And one of the bots we had, in fact, did try to use webmail. So instead of using SMTP, it would connect to Hotmail, log in with a stolen username and password, and then send mail. So in this case, we did set up a man-in-the-middle server to look at the credentials, but this was, again, a very small botnet which did not do a lot of spam, so it wasn't a big deal here. So what we have here are two really interesting streams of data, right? On one hand, we have our bots in Botlab, a few dozen of them, which are constantly churning out 6 million emails a day. And what's great here is that with these captive bots, you get to see spam, all the emails sent irrespective of destination. You see spam sent to Hotmail, Gmail, Yahoo, you see spam in various languages, and so on, right? So we essentially have a tiny slice of each botnet, and this gives us a very local view of the spam producers, but a global view of all the spam that is being produced, because you see kind of a wide variety of spam sent to all places, right? And on the other hand, we have spam coming into the University of Washington. So this is another 2.5 million emails a day, which provides a completely different perspective. So here, we receive spam from pretty much every bot node in the world. So if you have an infected machine, it is likely sending you spam. Over a couple of days, you would definitely see spam from pretty much all the infected nodes out there. So this kind of gives you a global view of the spam producers. You see all the spam producers, but a very local view of the actual spam, because you only see spam that is coming in to the University of Washington. So you only see spam coming to washington.edu. It's mostly English spam, mostly targeted at students, perhaps. And so this gives you a local view of the...
So that second mistake that you receive from almost every bot in the world, I mean, I guess I would challenge that in terms of, my assumption is, you have a relatively small number of email addresses from the entire world.
Around 1%. Or, yeah, it's around 300,000 email addresses.
Yeah, that's way less. I mean, come on.
0.1%.
Wait, 300,000? No, what?
300,000 email addresses.
Out of a billion? Couple of billion? I guess I'm wondering.
So we essentially see spam from...
I would assert I would accept that you see from a large number.
A large number.
Bots, but I wouldn't necessarily assume it was every bot.
Not necessarily every bot, but we do see on the order of 1 million IPs a day. So that is a fairly large number. Let me rephrase by saying a fairly large number of these bots.
Okay, well, so if you see 1 million, I would bet out of 1 billion PCs, more than 1 million of them are on botnets.
This is 1 million a day. And over a reasonably long period of time, you would see a larger fraction.
Have you compared to any external data feed? And you could certainly go to, say, Spamhaus or one of the open public lists of spams and spam websites to see what fraction that you're getting visible to you versus what's being observed in the world.
The problem with Spamhaus blacklist is that you don't really know the number of false positives and false negatives in there. But from a comparison, what we found was around 30% of the IPs we actually observed were present in Spamhaus.
Right, it's the opposite number that you really want to know.
So you don't really know what coverage Spamhaus would have either, right? Especially since we have no idea of the false positives and false negatives.
This should fall out statistically. I mean, right, if you know that maybe 5% of Spamhaus is false positives, and you know they're seeing 100 million IP addresses, and you know you're seeing 2 million, then you know you're seeing 2 million out of 95 million.
Spamhaus blocklists they're not in the 100 million range though. I believe, so I do have access to the Spamhaus blacklist, and they're roughly in the 3 million IPs on a daily basis.
Okay.
Is what you see, and this kind of changes over time as things drop out and things get re-added in. So the Spam House blacklist, which we looked at, had on average around 3 million IPs a day.
Did you compare your numbers with the one running by ICSI and the UC San Diego? They published some results on their spam honeypots.
Yes.
So
we do share our information with them, but this was done before their honeypots came up.
No.
Or
this is published in 2009.
2008.
2008.
So this
their first paper talking about spam architecture.
Spam analytics was before that, yes. But their actual spam, but that was a incoming spam feed, right?
Yes.
Yes.
But this one you're talking about incoming spam.
Yes. Right here was incoming thing.
Yeah. So I'm just saying about the numbers for incoming spam, like how many IPs they see every day, how many spam they receive every day compared to
that. I have not really chatted with them about their actual numbers versus ours.
So they didn't report in their paper?
Their paper did not have the number of IP addresses. They were looking more at the hosting of the spam campaigns, so things like where are the web servers hosted and those kinds of information, not the actual number of emails which they received. So one point here is that by combining these two feeds of information, you're going to get a lot more than any of these individual feeds, right? And the question was, how would you go about linking this? And what we observed from our data was that spam subjects are reasonably special. So they're chosen quite carefully for two reasons. First, they have to escape your spam filters. And second, they have to be interesting enough for you to want to click on them. So as a result, from nearly 6 months of our data, we found that there was absolutely no overlap in the subjects between two bots. So this was on an average of 500 subjects per day per bot, and we found zero overlap across any two botnets. So we decided that looking at spam subjects and comparing them would be a good way of linking these two different streams of data.
Spam that gets caught by the EW spam filter.
Yes, we do not have access to the other emails.
Well, right, but it's composed of less than 1% of the email coming in EW. You said 99% was caught by spam filter.
90%.
Okay, so the remaining 10%, 90% of that might be great spam that's escaping your spam.
Yes, that is possible, but we don't have access to that data.
And those might be other botnets that are composed
Definitely.
entirely of alternate means. Okay.
Absolutely. There might be different botnets, but in terms of actual total volume, it would still be a smaller fraction, though they might be more effective.
Yeah, it might be infecting PCs far more often
Yes.
that are spam. Okay.
How many spams botnets do you check? Can you classify based on all the all the millions of emails? How many?
Right. That will come up in the next couple of slides. The number of botnets we found. So from this linking these two streams of information, we decided to ask a couple of questions. There are more questions in the papers, but for now I'm just going to look at who's sending all the spam and what are some of the characteristics of these botnets. Right. So the first thing we found was that nearly 80% of all the spam came from just 6 different botnets. Right. And a single botnet called Shrisby was responsible for almost 35% of the spam. So this kind of means that if you could knock a few of these botnets out, you are going to significantly reduce the volume of spam on the internet. And the question now is, how difficult is it to actually knock out a botnet? So for that, let's look at a couple of characteristics of these bots. So the first thing we observed was that most of the botnets we ran contacted only a very small number of CNC servers, on the order of a dozen. And in many cases, the information about which IP address to contact is hard-coded in the binary. So if you could essentially block access to this IP address, the bot would be headless and would have no idea of what to do. Right? And in fact, in November 2008, hosting company Macolo, hosted in California, was taken down by researchers and law enforcement. And overnight, the volume of spam decreased by almost 80%. And the largest botnet, Shrisby, was completely knocked offline and never came back. Right? And so some of the other interesting characteristics that we found about these botnets was that you could possibly fingerprint which botnet is sending a mail based on the spam sending rate. So this varies from 20 messages a minute to crazy 2,000 messages a minute. Right? And we also looked at kind of mailing list overlap across two botnets. So if you're a spammer, you would preferably want to rent out multiple botnets to reach a wider audience, because 2 botnets, the overlap in mailing list was only 30%. And finally, we also looked at the active sizes of these botnets, and that varied from 16,000 to 130,000 with respect to how many of them are actively sending spam on a daily basis.
How do you get the size of a botnet?
Based on what we see, based on our incoming spam. So every piece of spam that comes in, we can, for 80% of the spam that comes in, we can say which botnet it belongs to, and by looking at how many different IP addresses we see. So this is definitely a lower bound of the number of spam bots.
These characteristics, so it seems that at least the first 2 of them are not fundamental to a more intelligent botnets. Right? So most of this, maybe because they have such large volume, they don't even care to be caught by anybody.
Right.
So there may be more smarter botnets which don't have to contact a fixed set of IP addresses, don't have to send this many, they can adjust their sending rate.
At least, so back in the day, most of the botnets we looked at had very simple central control mechanisms. Right? They would contact one fixed IP address or a bunch of IP addresses. And that has kind of changed slowly over time. And it still has not moved to a decentralized control network. It was only the Storm botnet which used a decentralized network, but all the other botnets, even today, still use a simple HTTP central controller. The way they access the controller has changed. So now instead of contacting a particular IP address, they use a DNS name, which is algorithmically generated. So each day it would generate a DNS name and look that up. And one of the problems with these approaches is that if researchers reverse engineer this, what they do is they pick a date which is, say, next month, and they buy that domain name. And so on that day, at least you've got control of all the bots. So a simpler mechanism would ensure that there is no infiltration, but they do have techniques to kind of spread out a bit.
So when you say most botnets have this characteristic, are these the biggest botnets you have?
These were the biggest botnets.
Yeah, I think, for example, the smarter, like the Storm botnet, maybe they only generate a small number of emails, a smaller number, but it's harder to detect, and they may be more effective because it evades most of the detection.
But so I think Stefan's group at UCSD actually did look at the Storm botnet. In terms of actual delivery effectiveness, it's the same as all the other botnets. They were not any more effective than the other bots. And they also had this additional problem that since their control network was decentralized as a part of a DHT, researchers who could simply easily infiltrate a DHT now had control of these bots and could make them do what they wanted. So it's kind of a trade-off between having full control and having reliability. And so far, it turns out that botnets have not needed to kind of branch out, and even today they still use a central controller with a small number of servers. And the main reason for that is that if these servers are not hosted in the US, if they're hosted in Eastern Europe or in Russia, it's really hard to take them down legally. And so this is sufficient for their current purposes.
Some of the best botnets are hosted in different countries.
Yes.
So how do you compare it? Like SpyEye, Zeus, some of the known attacks is going on right now in the financial industry right now. So there are botnets which are in the range of gigabytes. Some of them were taken down by some of the researchers in the past. How do you compare against them? Because you're saying it's centralized, but the existing research that's going on across different places are saying that it's not. It's running on a fastplex servers in a bulletproof host. So how do you compare against that actually? Because
so this is the way it was in 2008.
Okay.
And as I mentioned, as of now, things have kind of diversified a bit, but they still only contact a small number of hosts. They do not need to contact a large number of hosts yet because they're hosted in different countries. Right? So there is no legal framework which makes it easy to take down these nodes. So a small number of nodes is sufficient for them to get by. But naturally, they would diversify and have a larger set as you go. It's an arms race, which as you raise the stakes, they're going to try something different. And so this is the state of botnets as it was a couple of years ago. Okay, so what did we get with Botlab? So what Botlab gave us was a real-time feed of malicious links and spam that was being sent out. And this would be useful for having safer browsing because you know firsthand what the bad links currently going out are before they've been caught and added to safe browsing databases, and also better spam filtering, because now you have a pure feed of spam that is being produced. And this was used by, again, UCSD folks to generate a signature-based detection for botnet spam. And the details of command and control servers and the communication is useful for detecting network level botnet activity and also for CNC takedown. So the information from Botlab was provided to both law enforcement agents and also antivirus companies, so they can go about doing their business. Right? Okay. So now we've seen kind of the end result of what botnets do, right? And the rest of the talk is kind of going to focus on how they propagate and how they work. Yeah.
A lot of Botlab seem to be focused on spam sending bots.
Yes.
Some of the detection mechanisms as well as some of the results. Could you comment on other types of bots that do other kinds?
Right. So the other things which bots do, I mentioned in my initial slide where I said this is the bad stuff that happens on the internet. You've got click fraud, bots which do click fraud. You've got bots which send out phishing attacks. You've got bots which do denial of service attacks. The reason we picked spam is that it is easy to see both parts of the attack. You get to see spam that is being sent out, and you also get to receive spam. Now, this is not really true of click fraud. You need to be a search engine or a large advertising provider to observe click fraud from the other side. And the same thing with denial of service attacks. Unless you're a big company, you don't get to see denial of service attacks. So the reason we picked spam bots was so that you get both sides of the picture. And other bots are also similarly operated. In fact, a lot of these spam bots, they partition some portion of their botnet to do various activities, and these are rented out to people who want to do different things. And we do see some click fraud in the outgoing fashion, but we did not focus on it because we couldn't get a complete picture. But some of the techniques we use here could also be used for other kinds of botnets because they use a similar control mechanism.
So, based on the information provided by botnets, the previous slides, how to use botnet. So what about just we directly use the spam feed we got from Hotmail, any popular email server, and use their spam detection? It seems that this approach can extract the similar information that provided by Botlab. Like,
yes.
For example, which IP address it comes from,
right.
What are the type, the subject. So if that seems to be a much simpler approach than Botlab. So what's the advantage of Botlab?
So here you kind of get attribution. So over there you're going to see, okay, these are the botnet IP addresses out there, but you don't really know which botnet they belong to.
But as you said, they have different subjects, right? Based on the email subject, I can easily just classify.
You can cluster them, and that is something we learned from Botlab. So you don't need to keep running Botlab. You could use the information you gain from here in order to continue without it.
Okay, so
the fact that these spam subjects are in fact unique is something that came out of our running of actual bots.
Also, you use other signature to detect that the same bots have the same subject rather than just directly look at the subject and know that, oh, all these bots.
We also did look at other signatures in the SMTP headers, which kind of suggested that they were the same thing.
But SMTP headers, I can get the same information from the email spams directly as well, right? So
right.
What are the signatures that Botlab provides that are not present in the direct?
The only thing which we know is the set of subjects which are being currently sent out by each botnet. And we found in these subjects that these are unique. And this information can now be used even without the presence of Botlab. That is true. Botlab was kind of a bootstrapping process which let you understand how some of these bots operate.
Yeah, but what I mean is I can extract the same information about the botnet information from just directly getting the email server record. Like based on what email I get and use spam filter, I can know, oh, these email from the same bot have similar subject from the same similar SMTP headers. And why do I still need to run like the Botlab with a lot of VMs and doing this kind of thing?
You get to see things like other information about which are the command and control servers they contact, what is the control infrastructure like. So these are two different aspects of the information you would see. Okay, so let's kind of backtrack and see how it all begins. So the question we asked was, one of the things we found was that some of the mails which are used for self-propagation are things which servers which host malware are in fact legitimate sites that had been compromised. And the question was, how do attackers find these vulnerable servers on the internet? The question is, how do you find anything on the internet? You search for it. So one example. So here's an interesting thing we found was that search engines are really good at crawling and indexing everything that is accessible. And in many cases, a poorly configured server might expose sensitive information that can be then used by attackers. So attackers can then craft malicious queries which would give them this information. So let me give you a concrete example of what I say. So here is a posted exploit for a PHP-based content management system. So this is an application running on top of your web server. And this is an application called Data Life Engine. It's a content management system. And version 8.2 of this Data Life Engine has a remote file inclusion vulnerability, which means that any third party can store an arbitrary file onto this web server. Right? And they also helpfully provide a search term which can be used to find such servers, which in this case is powered by Data Life Engine. So this is essentially, so you find in all these web applications, say in the case of Data Life Engine, at the very bottom of the web page that is generated, you'd have this term called powered by Data Life Engine, copyright, trademark, and all the other things. You pop this into a search engine, in this case Bing, and you find hundreds of thousands of servers. Right? And some fraction of these servers would in fact be running version 8.2, which suffers from this vulnerability. So now you no longer need to kind of brute force search the entire internet for all potential vulnerabilities, but you have used the search engine to shortlist your search to a narrow set of things which you can now easily attack.
Good question. Where did you copy paste the top part?
That is posted on hacker forums. So you've got lots of these underground forums where hackers share their information, and you can kind of bootstrap your system from this. So overall, search engines kind of make it easier for bad guys to go about their business, right? And our goal here, given now that you know what kind of queries attackers use in order to find vulnerable servers, the question is, can we use this information to essentially understand how attacks happen and possibly detect new attacks before they are out in full force. So we want to essentially follow attackers' trails and kind of have them be our guides. And in order to do this, we had access to a great data set, which happened to be the Bing data set. So we had 3 months of sampled logs from Bing. This was over 1.2 terabytes of data containing billions of queries. Right. And so with SearchAudit, we have 2 stages. First, we have the identification phase, wherein we try to detect malicious queries. And this is an automated process where we start with a known seed set, expand it, and generate a list of all malicious queries. And the second stage is the investigation phase, where we kind of manually analyze these queries and try to understand the intent of the attackers. Let me quickly look at the identification phase. So here we start with a small set of known malicious queries, right? And these can be obtained from a variety of sources. In our case, we kind of look at hacker forums. So one of them is hack forums, another is Milworm, where they post exploits and the set of queries which you could use to find these vulnerable servers. We crawl these forums, and we start with a seed set of 500 queries. Now this was from a 3-year period. So we start with a small seed set. And now we have, on one hand, we have the set of seed queries which we know to be malicious, and we also have the search log, which is a set of all queries which were issued to Bing. And then it becomes reasonably straightforward to see which of these malicious queries actually show up in the Bing search logs. And once you have this, you kind of know who are the people issuing these queries. And one of the things we find about attackers is that they don't issue one query and stop. They issue a bunch of different queries. And so you kind of now have a larger set of queries which you did not find in your seed set, but are able to find through the search logs. Right? The next step is to generalize these queries. So one of the observations we made was that attackers don't use the same queries verbatim. They make changes to suit their needs. So one of the things they do is they sometimes say they restrict the domain to which they want the search results to be returned for. So they might be only interested in .edu domains which are running a particular site because they have a higher page rank and are more valuable for their time. And in some cases, we find them adding random keywords throughout the query string so that you get a different set of search results. And an exact query match, an exact string match does not capture these variations, so we decided to use regular expressions. In this case, we feed all these queries to a regular expression generator. This was AutoRe, which was in SIGCOMM 2008 from folks at SVC. And this kind of helps you capture the structure, the underlying structure of the query, and you get to match all queries which are roughly similar, even though they're not an exact match. Right? And here's a regular expression tool, and once you have this set of regular expressions, you can run this on top of your search log, and you find all the various queries which are similar. And now, once you have this, you can think of this as your new seed set. I mean, these are all malicious queries. Why don't you repeat this process? So we essentially do that till we get a fixed point where we feed this back into our system and look at this query expansion, and we find our final set of malicious queries. And typically, it converges in 1 or 2 iterations, and it wasn't a big deal. So this is some of the data we have from a week in February 2009. We found these sorts of malicious queries from nearly 40,000 IP addresses. They issued 540,000 unique queries, which are all different, and for a total number of 9 million queries. So this number comes from the fact that many queries are repeated multiple times in order to get different pages of the search results. So they'd issue the same query and look at the second page, issue the same query, look at the third page, and so on. And so in a week, we found nearly 9 million queries for these kinds of vulnerable sites. Right? And what kind of attacks did we find from these queries? So this is a part of our analysis phase where we looked at these queries to figure out what they're looking for. And one of the things we found that naturally they were searching for vulnerable web servers, and we found that nearly 5% of the returned search results show up in blacklists at a future point in time, and 12% of these returned servers were in fact vulnerable to SQL injection. And we also find queries which were trying to find forums and blogs to post spam comments on. So you'd find queries of the form so-and-so blog, add comment, or add post. Yeah.
Regarding the first one, so if my query is only for powered by something, that's actually return all the websites that run that software, but with different versions.
Right.
Some versions are vulnerable, some versions are not.
Yes.
So in terms of just finding the query, that doesn't give you a precise set of rules to identify vulnerable web servers.
You're going to see a bunch of these queries, and there are some other queries which look at it's not just what is powered by, they also have things which are specific to the path. So a particular, say WordPress 5.1 uses a particular set of paths in the URL.
So what I'm looking for, do you think you can generate a set of vulnerable web servers just simply by analyzing the queries?
Of potentially vulnerable web servers. They're not all vulnerable.
Potentially, that means they could have a lot of false positives.
Yeah, so in our case, we found only 5% of them actually show up.
And your 5% actually is based on the future, some future event you can do a cross-check.
Yes.
When you actually trying to infer that, that means a large number of them are not vulnerable.
They are not necessarily vulnerable, but they are being targeted by the attackers because they are issuing these queries with the intent of trying to compromise them.
Yeah, but okay. But basically you cannot.
You cannot say for sure whether something is vulnerable purely on this.
Okay.
Just a quick question on this previous iteration. So you have those initial dorks, and then you expand this dork set. So how big was the set in the end compared to those initial dorks that you found on Malware, for example?
So the initial dorks was 500 queries, and the final one was 540,000.
Okay.
But they're all kind of variations of similar dorks.
Right.
In many cases, they are other dorks which the attackers issued, and in many cases, they are variations where they add these things at the end and beginning and random keywords.
But you said you also expanded, based on what else they were searching for.
Yes.
Based on IP address, I assume. So essentially, this would not terminate and get you the whole Bing index, right? I mean, how did you distinguish between this is a dork and this is just an IP that looks up a string on Bing?
So only the ones which started with these dorks, right? So we look at only IPs which issue at least one of these dorks,
right.
And we look at the other dorks that they issue, other queries that they issue.
But say I'm an attacker, I Google for a dork, and then I want to search, what's in the restaurant food bar today. So then I would get everything from
right. So we also we also do look at at least a large number of people who issued similar queries. There must be some overlap criteria that had to be done. So we do a bit of filtering before we don't blindly take all the other ones. We do a bit of filtering which makes sure that doesn't happen.
What's the baseline for your top bullet?
Baseline in the sense?
You said 5% are in blacklists. If
Yes.
I were to just randomly sample web servers on the internet,
0.5%. 0.5%.
0.5. So this is a
10x.
10 times more likely to be on a blacklist.
Yes. 6 to 10 times. It varied from 0.5% to 1%.
Okay.
So that was the baseline. And for SQL injection, we found 2% to be vulnerable if you search for a random query. And one of the other attacks we found was actually an ongoing phishing attack of live messenger user credentials. So you had attackers who would compromise a live messenger user and send out a phishing link to the user who would then click on it and be shown some things, and his account would also be compromised. So looking at the search audit results, we found nearly 1 million such compromised accounts over a period of a year. And this was something. Yes.
I actually had to get 400 domains. How did you get 1 million compromised accounts? And maybe it's out of scope, but
so the way it worked was that when you click on one of these links, what happens is that it issues a query to Bing. The way they set it up, this was purely incidental. It is not anything specific to this attack. It just happened to make use of the Bing search engine. So it would issue a query to Bing with the referrer field containing the username of the person who clicked the account. And that's how we were able to see which are the set of users who had been compromised. And then we also did some later cross-analysis which showed that these accounts had in fact been accessed by the attacker from an IP in Singapore and kind of verified that these were in fact compromised. So with search audit, what you get is as soon as an attacker starts his process of finding these vulnerable web servers, you know which are the servers that are in the crosshair. So you can potentially proactively defend against these attacks even before they are launched. And the search engine could try to block such malicious queries or sanitize these results to make it harder for the attacker to go about finding these things. So eventually we can use it to detect new attacks as they come up and potentially also find attackers. Right. So the next step, once you have this notion of which are the servers being targeted, what we decided was how do you know what attackers do next? What is their next step? How do they actually go about compromising these machines? And in order to do that, we take a page from the attacker's playbook. We create fake pages that look vulnerable. And these pages are now crawled by the search engine. And when attackers issue these queries, they get our pages. And when they try to attack us, we get to observe their attempts firsthand. So let me quickly run through the architecture of these heat-seeking honeypots, which kind of give you this information. So first, we have the malicious query feed, which we get from SearchAudit. So we know the set of queries which attackers are issuing to search engines. We issue the same query to Google and Bing, and we get these pages. We fetch these web pages and store them and set them up in our honeypots. These are now crawled by all the various search engines. The next time an attacker issues a query for a similar term, our pages get returned. And then they kind of try to attack us, and we get to see firsthand how they go about this.
Your pages will be returned way down in the relevance ranking, right?
Yes.
And so, why? What?
Because they want everybody.
A billion? It's automated. So even though you might be the 10 million target.
On the 1000th page, we still get it. And since we have people on .edu and Microsoft.com linking to our honeypot pages, the rank is a little higher than it should otherwise be.
You legitimized your space data.
Yes. Okay. So once they find these attacks, we kind of installed an actual software to see how the compromise really happens. And the actual compromise is nearly trivial, almost straightforward. So OS Commerce is a web software for managing shopping carts. If you're running a Amazon-like website, if you want to have a shopping cart, you would use OS Commerce. And if the site is hosted on example.com/store, the way you would actually compromise the site is straightforward. You would visit this URL and present a file for them to upload, and now it is hosted on your web server. And this could be any file. It could be an executable file. It could be a PHP file, which can essentially run with the privilege of your web server. And what they do after this is quite interesting. Most attackers typically host a PHP-based file management system. So it's like a shell, which gives you a graphical interface to delete files, upload files, change permissions, perform a brute force attack of your /etc/password file, and whatnot. So this is typically one of the typical things that attackers do after they've compromised the server. And then they can host any amount of malicious files on here and then send out links. So from our honeypot, we set up nearly 100.
Does the web server run in change root or something, so it can't get at your executable?
It does not, at least for the smaller web servers. So naturally, the ones which are attacked by this are not the very well administered ones. These are free open source software and usually run on smaller servers without a good security policy. So we ran our honeypot for 3 months, and with 100 pages set up, we found nearly 6,000 different IP addresses visiting our page. So not as large as it would have been if we had a highly ranked site, with nearly 55,000 attack attempts. And our honeypot saw all sorts of different attack attempts, such as trying to gain admin access, brute force password attacks, SQL injection, cross-site scripting, and the whole gamut of things. Yeah.
The attacks were a result of the honeypot as opposed to just random. In other words, I run a number of web servers that are constantly just getting scattershot.
Right. So we do have a baseline case of just Apache running there, just a web server, and we see 5 different attacks, whereas with the honeypot we see a larger variety of attacks.
How do you run it side by side?
This were 2 different. This was like before and after.
But 2 different IPs, right?
Yes,
at 2 different times. So
no, at the same time, 2 different IPs.
But 2 different IPs. But the IPs are right next to each other or something?
Yeah, they're all in the same domain. They're all in Washington.edu. Right, and now for the last part of the thing, which should be pretty quick. Here, so what happened after the site was compromised was that they host malware pages on there, and then they spread these links through either emails or IMs, or in this case through search engines. So let me give you a video example of how this works. So if you go type in a query in Google, which is a benign query, in this case say Flintstones pictures on MySpace, and they happily help you autocomplete, search in the results, click on the very first link, and that turns out to be a compromised link, because now it shows up a big pop-up which says that your computer is infected, and you click OK. It scans your Windows drive, your C is infected, D is infected, you've got a whole bunch of things going on, and now you have a choice of either protecting your PC or ignoring it. No matter what you do, it tries to download a file, and if you actually save and install the file, you have now been compromised. So this is a rather common form of social engineering, which today is called scareware attacks.
You're running that on the Mac?
No, this is actually Windows.
Oh, it's a video.
This is a video.
It says the browser's like serving your operation system.
Yeah. So this, it runs on a Mac too. You get the same thing, but the full screen doesn't look quite so realistic, so I had to run it on Windows to take the video. Now, is this really a problem? Well, it turns out nearly half of the popular search terms contain at least one malicious link in the top results, and that is quite bad. And just last year, this sort of scareware fraud cost nearly $150 million. Now, where is the money coming in? Well, once you install this fake antivirus, it runs in your taskbar, and every 30 days it pops up a link saying your protection is running out, please buy the full version for $30. And turns out at least 5 million people did fall for that and paid $30 to buy it.
The scareware doesn't take over machines, scan all your files, and blackmail you. It just tries to sell you.
So this one does not, but you do have things which also.
It's software.
Does nothing.
There is a similar thing which does ransomware, which would essentially encrypt your C drive and then ask you to wire over so much money before it gives you the password.
When you say top, you mean the top 10?
Top 50.
Top 50.
Yeah. And this was mostly a problem with Google, not with Bing. So it's good
I
thing.
feel like it's stealing a Ferrari and getting an oil change or something. It's just this weird. Okay.
So I guess they could also use it as a dropper, because once you've installed a piece of software, it doesn't have to be just this fake antivirus. It could be anything of their choice. For now, this seems to be a good monetization approach that they have stuck to. So goal here was kind of to understand how these search results are getting poisoned. How is it possible for them to, within a day, poison a top news result and get it to the very top of the search results? So for this, we actually looked at a sample attack. This was a real attack which was going on in progress. And this contained nearly 5,000 compromised web servers. And these have a very strongly connected cross-domain link. So you have each of them pointing to 200 other sites and so on. And these guys, once you click on any of these results, it redirects you to an actual exploit server which serves this malware exploit. And these were hosted on nearly 400 domains in the US and in Russia. And one of the things we observed, one of the things was that the log files on these servers were not really well protected. So we were able to access these logs, and we could see which were the different things they were redirecting to and how many victims actually clicked through. And over a 10-week period, we found more than 100,000 users had actually clicked through to the final scareware page.
When you say they weren't well protected?
They were not password protected. The log files were on the web server and could be read. So we didn't have to do anything shady to access the file.
So, like that ethical? I mean, is that part of the no crunch, no crawling, under the no crawling? Like by default, you can download the other another Apache server's access log.
This is not the Apache server access log. This is a log stored by the attackers.
The attackers decided just to make it a request where you don't have to authenticate, so you didn't have to pretend to be them, you didn't have to do anything other than just say, may I have it?
Exactly. It was I would say, a capability based. If you know the name of the file, you can access it.
It's opportunistic. It's basically opportunistic. The attacker happened to store a log file on the server that everyone can access with no protection at all.
Exactly.
Okay. What do they care?
Yeah, they don't care.
So those are the log servers on those 500 servers, right? On the exploit?
Actually, they're log files on redirection servers.
Okay.
So all of these 5,000 servers funnel into 3 servers which are responsible for redirecting to the final server.
Okay.
So
have you ever verified those log files? Because I mean, what's public at the moment is that you have interfaces or log files just basically producing random output. So if you go there today, it will say 100,000. If you go there tomorrow from a different IP, it will say 13.
No. It was definitely verified. I tried it from multiple IPs, and every time I visit it, my IP and everything also gets logged.
Okay.
So some of the prominent features for this attack were that nearly 20,000 keywords were poisoned. And where do the attackers find these keywords? They come from Google Trends. And so Google Trends is essentially each day Google produces a list of the top 20 search terms. And now these hackers take these 20 search terms, they push it into Bing, and for each of these terms they get another 10 related search terms. And they collect all these things over several days and now have a huge set of keywords that they can now poison. And more than 40 million pages were indexed, and all this happened in just 10 weeks. So in order to detect these things, we make use of the features that we found. So one of the things we found is that they have a very dense link structure across them, hundreds of sites linking to each other. There are many popular search terms in the URLs. Pretty much anything related to Justin Bieber would show up there. And then there were a large number of new pages. So once a server got compromised, you'd find that an attacker now suddenly hosts 1,000 or 10,000 new pages on the server. And that these new pages are very similar across multiple domains, since hackers typically use scripts which go out, attack, and host these servers. They're very similar across these domains. Yeah.
But there's a long history of related work of fighting against SEO.
Yes.
I mean,
so this is not particularly SEO. This is more towards only the ones which are for compromised sites. So SEO typically is for sites which are set up for this purpose. But compromised sites, you have a different view of the model. They have a particular behavior up to a certain time, and once it gets compromised, they completely change phase and do something different.
No, but put it the other way, right? For an attacker to put a compromised website into your top results, they would use similar techniques so non-malicious websites are trying to optimize their search engine result will use a similar techniques, right? Then you can, so in that sense, your techniques to detect SEO optimized compromised websites will be similar to search engine to detect SEO optimized benign websites.
Yes, but in our case, it's probably a little easier because there's a sudden phase change after the compromise. So we can make use of that to determine which sites have been compromised.
I see. You're assuming you have a before and after.
So we have the web logs from the historical information about each website.
I see. Okay.
And so it's actually easier than the normal SEO thing which search engines have to do.
I see. I see.
And some quick results. We found nearly 15,000 URLs and 100 domains for corresponding to multiple compromised SEO campaigns. And there were, we picked 120 popular searches, and we found that 43 of those searches did in fact have compromised results, and 163 URLs were compromised. And to conclude, today's landscape is rather complex, and we need a multi-pronged defense strategy to address these various attacks. So we built SearchAudit, heat-seeking honeypots, DSEO, and Botlab as defensive tools. And we found that monitoring attackers often reveals new attacks, and that infiltration is a rather effective mechanism, but has to be done carefully. And with that, let me just quickly mention, I've also done a bunch of non-security projects. So a couple of them are consensus routing, which kind of does consistent routing on the interdomain level. And I also built Hubble, which is a system for studying reachability problems in the internet. And more recently, Keypad is a file system for theft-prone devices. And if you want more information about bots, you can go to botlab.org. And that is it. Yes?
You alluded to it. In the slide, you had the 120 searches on Google with 43 found with malicious.
Right.
What about Bing results?
One. Bing had one result.
Are you going to publish that somewhere?
Oh, yeah, it was there in the...
Yeah, we've been doing it for like a year. I mean, the Bing guys have been working.
It's there in the paper.
Those out, yeah.
It's there in the paper for sure. And yeah, Bing had only one malicious result, but Google did.
For scareware or for any compromise?
For spam links. In our case, we are looking only at this sort of compromised SEO.
I guess this is a problem throughout parts of solutions, but very clearly it's coming out in the DSEO case. None of the features that you have detected to identify cases of SEO being done from this seem to be necessary, because the fact that there are a large number of pages or a large number of new pages or new pages that are similar, you could, if somebody knew that by doing that they would get filtered out, they would work around it. So it didn't seem like they're necessary to...
A couple of necessary conditions there are the dense link structure, because finally it depends on the PageRank algorithm.
But what if I just have some random links to get rid of the dense link structure? I mean, even that doesn't seem necessary.
No, if you just look at the dense link structure across these things, if you look at the completely connected or the strongly connected components, that is kind of necessary in order to boost your PageRank. You need a lot of incoming links.
It kind of depends, right? If you only have 100, maybe you need strongly connected. But maybe if you have 10,000 or 20,000, you would still boost up without being strongly connected among your set of... all you have to do is to get down to the level of strongly connected that a base sample will have.
Right.
And yeah.
So yeah, in that case, it is not necessarily... It is possible for them to move things around, but in terms of getting it up to the top very quickly, they do need things like they need relevant information in the page, right? For you, if you just focus on these top search terms, that is sufficient for you to kind of look at a smaller set of web pages and then do your analysis on there. So one of the things which they found necessary was to be a relevant search term, because there is not much historical information about these things. Like, it's really hard to kick Bank of America out of the top spot, but something about, say, the tsunami or something else, it is really, the search engines don't have any historic information about these things, and so it becomes easier to game the system for these short-term events. Yeah.
Another way to, I don't know if this would work, but another way to distinguish your apparent SEOs from companies that are actually trying to optimize search engines is if in one case, if you email the site administrator, they will say, oh my God, my site's been hacked. In the other case, they'll be like, well, that's the way it's supposed to look. We've got a great site. It's got all sorts of content. Would that work, or do most site administrators just not respond?
Most site owners do not respond. So one of the things we had was, once you recognize the site had been compromised, any attempt to contact them would place some sort of legal liability. Because in many cases, they would be like, oh my God, Microsoft attacked me. So if you send a mail from Microsoft saying your site appears to be compromised, that is kind of a reaction they would have. And so the lawyers were like, yeah, if you find something, just don't do anything.
Did you rely on the log?
Send email from Gmail.
Did you rely on the log of Bing has, the crawl log for a website
Yes.
they stored like a month ago? Something?
Yes. So we made use of the historical Bing web information.
We should put a website of all the compromised sites.
Huh?
We should put up a website of all the compromised sites, and then they can go and look.
That's slander.
Oh, that's slander.
The same way they do spam blacklists.
Anonymous email?
Yes.
So this is more for the audience, but I mean, I'm assuming most people came here because they're interested in botnets and research on that. Do we have an internal DL for discussing this kind of thing? Should we? I guess there isn't a deal. How many people are interested in a deal for this kind of discussion? Not that many, okay. Okay, well maybe we should just get together when this is over. Share notes, get something set up.
All right, let's thank the speaker one more time.